Fundamentals for design of rectangular beam. I will try to make a brief regarding the basics. When a simply supported beam is loaded from top, it will undergo sagging. When a cantilever beam is loaded from top, it will go under hogging, right? In case of sagging, the tension is at bottom and compression is at top. And in hogging, compression is at bottom and tension is at top. Okay. So as concrete is weak in tension, we provide steel in tensile phase, right? So we here, for this case, the main steel will be at bottom and top steel will act as an hanger to keep the stirrups in position. Similarly, in this case, main steel will be at top, okay, and bottom steel will act as hanger to keep the stirrups in position, right? Assumptions for analysis and design of RC beam. Plane sections normal to the axis remains plane after bending. So this is before bending, okay. This is a section normal to the bending axis, and that is this over here, okay. After bending, this is the plane section, which is this, okay. So this is how we get the strain diagram, right? So the ultimate strain in concrete is 0.0035. After this strain, the concrete starts crushing, right? And the ultimate strain to be taken in steel is 0.002 plus 0.87 Fi by ES. The strain in steel should be equal to or greater than this. Then only we will get an tensile failure, right? Okay. The design stress strain curve for concrete is as shown over here. This is force C, this is force T, and the lever arm is the distance between these two force, right? So T is equal to Fi into AST. When it is an under-reinforced section or a balanced section, then Fi is equal to 0.87 Fy. That is design stress, right? And C is equal to 0.362 FCK P into XU. B is the width, XU is the depth of the neutral axis, okay? Okay, the tensile strength of concrete is neglected. And in case the partial safety factor for concrete is taken is 1.5, and that for steel is taken as 1.15. Okay. Basic criteria application for Fluxion member as per IS 456-2000. The concrete grade for nominal cover should be provided as per table 5 and 16, which with respect to the weather exposure conditions. The effective span of Fluxion member should be found as according to clause 22.2. The effective depth should be calculated as per clause 23. The slenderness limit for beam to ensure lateral stability should satisfy clause 23.3. The minimum area of tensile steel AST minimum is to be found out by this formula 0.85 BD upon Fy. Maximum percentage of steel allowed for both tensile steel and compression steel is 4%. For beams with or without torsion, side reinforcement has to be provided as per clause 26.5.1.3. Okay. Check for shear is necessary. Check for deflection is necessary. Steel detailing is to be done as per SP 34, and over reinforced sections are not allowed. Okay. Right. Now design all the beams of the space frame shown below. Use M20 grade concrete and Fe415 steel. Take effective cover equal to 50 mm. Allow below table shows the effective span and effective depth of beams. Width of all beams to be taken is 230 mm and depth of beam to be taken is 525 and 300 mm as the suggestion of the architect. Okay. Applied loads are total factor loads, that is dead load plus live load. Okay. So this is our 3D frame. Okay. These are the beams which are to be designed. Okay. So B1, this is B2, this is M1, M2, B5, B4, and B10, B9. Okay. The center to center distance, that is 5 meters. Okay. That is our effective span for this beam. Okay. And in this direction, this is longitudinal direction, and in transverse direction, the effective span of the beam, that is center to center distance of the beam, okay, or you can say effective span of this beams in transverse direction is 3 meters. So this is the bending moment diagram. This is the shear force diagram. Okay. Now this is the table. These are the beam numbers. This shows the width of the beam. This shows the depth of the beam. This is the effective depth of the beams. Okay. BO consider effective cover as 50 mm. So effective depth will be 525 minus 50, that is equal to 475, right? This is the effective span. These are the effective spans of all the beams, right? Okay. Now, important note I have made over here. To start with, is assume the depth of beam a little bit higher, rounding off to span in mm by 10, right? So say this is 5 meters, so this is 5000 mm divided by 10. So you can take effective you can take overall depth round about 500, so I have taken as 525, right? When the span is 3 meters, that is 3000 divided by 10, you can take the overall depth as 300 or nearby that. I have taken 300. So this is how you can assume the depth of the beam before starting the analysis. Okay, which is usually found to be okay in the design criteria. Okay. Now these are the beam numbers with their size. Okay. Okay, this is negative moment about left. Okay, negative moment about left. Let us take b1, right? This is b1. So negative moment about left, this is hogging moment, right? That is 53.35. Then maximum positive moment 67.83, that is over here. And this is negative moment about right. Again, this moment is negative because this is hogging moment, 127.92. So this is 127.92. Shear force at left, shear force at left, shear force at right, shear force at right. Okay, and this is the twisting moment. Okay, so this is the twisting moment in this member. Okay, so this is summary of the bending moment, shear force and twisting moment of each members, that is beam members, flexure members. Okay, we can see over here that the twisting moment is almost zero, right? Over here in beam 3, we can see the twisting moment is maximum, that is equal to 2.1 kilonewton meter, and in beam 8 it is 2.1 kilonewton meter, right? Otherwise it is almost near to zero. Okay, so if the twisting moment is very small, we will neglect torsion in design. Okay, as the twisting moment are very small, so we will neglect it in design and design all the beams as regular beams without torsion. The moment obtained from 3D analysis, that is this, and 2D analysis as shown below. In 2D analysis we have ignored torsion, okay, torsional stiffness. Okay, the results are found to be almost same. Okay, say b1 b2, right? This is this frame. Okay, b1 b2, this is this frame, right? The 2D analysis of this shows that the moment at the left in b1 is 54.37, here we get 53.35, at center is 67.48, here we get 67.83, and at right hand support it is 127.43, here we get 127.92, right? So the results which we obtained through 3D and 2D are very near or match very near to each other, right? So it is but natural that we can ignore torsion in this case. Okay, right. Following is the formula to find the limiting moment of a section. The design moment should be less than the limiting moment, as the section has to be a singly under reinforced section. Otherwise the section has to be designed as balanced doubly reinforced section. Okay, if your design moment is found to be greater than the limiting moment, then the section will be over reinforced, right? So to avoid the over reinforced section, it is better that we design that section for as a balanced doubly reinforced section, right? Okay, mu limit. So we have two types, two sections, okay, of beams. One is 230 by 525 and another is 230 by 300. So we will have to find MU limit for both the cases, okay. So MU limit when beam size is 230 by 525, we know this formula: 0.138 FCKBD square for M20 grade of concrete and Fe415. Our effective depth provided is capital D minus effective cover, 525 minus 50, that is 475. So MU limit is equal to 143.22. If our design moment is found to be greater than this, then you will have to design that section as doubly reinforced section. Okay. Now, once you know MU limit, so MU limit is equal to T into lever arm. Okay. Simple from the statics. Force T into lever arm is equal to MUR, that is the moment of resistance of this section, right? T is equal to 0.87 Fy AST, we know that, right? And this is lever arm. This lever arm is D minus 0.416 XU. XU is the depth of the neutral axis, okay? So from that we get this formula, okay? Simple. AST limit is equal to MU limit divided by 0.87 Fy into lever arm. Okay, this is D minus 0.416 XU. For a balanced section, XU is equal to 0.48 when for Fe415. Okay, so this is how we get the limiting moment. Limiting AST, right? That is 1043.5 mm square. Similarly, limiting moment for the section 230 by 300. Okay, over here the effective depth we have provided is 250, that is 300 minus 50. So MU limit is 39.675 and AST limit is found to be 549. This is for size section 230 by 300. This is for size section 230 by 525. Okay. Now we know this formula. This is very familiar to us, that when the section is singly under reinforced rectangular section, then you can use this formula for finding AST directly, right? In our case, FCK is 20, Fy is 415. Okay, code is given this formula for finding AST minimum in case of Fluxion member, that is 0.85 BD upon Fy. If it is a T-beam, then instead of B you have to take BW, that is instead of B you have to take BW. This B is width of beam, and in T-beam it will be width of web. Okay, so when D is equal to 475, that is beam size is 525, overall depth and effective depth is 475, we get minimum steel area is 224, and when D is equal to 250, then we get the minimum steel area is 118. Okay, so the steel provided should not be less than this and should not be greater than AST minimum. Okay, if the steel is found to be greater than AST minimum, AST limit, sorry, and then you have to go for doubly reinforced section. Okay. Okay, calculation of steel. So these are the beam number and their size. These are the moments, negative moment at the left end support. Okay, so when you put this moment in this formula, you get the steel, right? This is a steel that has to be provided. Okay, now we will round off this and we will, so you can say this is still required. Okay, and we will round this off and provide this much, right? So over here the required steel is 333 mm square and we are providing 402 mm square, that is 216 mm dia bars. Okay, so this 402, when the size is 230 by 525, that is we have to see over here, right? This 402 has to be greater than AST minimum and has to be less than AST limit. Okay, so it is less than AST limit and greater than AST minimum. So it's okay, it's fine. The section is singly under reinforced section, right? So this is how this table has been created. Okay, so this is the maximum moment, positive moment near the midspan. This is the required steel, this is the provided steel. Okay, this steel is provided by putting M in this formula. Okay, similarly this is negative moment at the right hand support, negative because this is hogging. Okay, this steel is has a sign negative because it is in hogging moment, and your steel that is to be provided is at the top. Okay, at support, the steel means steel tensile steel will be at the top, so it is denoted as negative AST, right? Over here also it is denoted as negative AST because at support the tensile will be at top, because this is a hogging moment, so tensile will be at top and you will have to provide your main steel at top. Okay, so this is how this table has been populated. Okay, now we will start the design of beam. Okay, so first we will take design of B1, B2, B9, B10. Okay, that are these beams. B1, B2, B10 and B9. Okay, these are identical, so we are taking it together. Okay, so beam number, their sizes, a negative moment at left hand support, steel required, steel provided, positive moment near the midspan, steel required, steel provided, negative moment at the right hand support, steel required, steel provided. Okay, so this is how we find the longitudinal steel. Now let us see the detail of this. Okay, we'll see it for B1. Okay, for B1 on left hand support we are providing 402 mm square, that is two number of 16 mm dia bars, right? So let us see the detail. Okay, so this is B1. Okay, left hand support we are providing two 16 mm dia bars, right, for a distance of 1.2 meters, 1.25 meters. Okay, similarly, okay, this is the required. Okay, but we are providing, let's see, I will try to explain. Okay, over here we are running two 16 mm dia through and through. Okay, throughout the beam. I will explain that. Okay, but just for explanation, at support now you can see that we have provided two number of 16 mm dia bars. Okay, then at midspan, okay, we are providing 452 mm square, that is four number of 12 mm dia bar. Okay, at midspan four number of 12 mm dia bar. Okay, then at right hand support it is 316 plus 120 mm, that is 917 mm square. 316 and 120 mm dia bar, right? The same thing is repeated over here. Okay, right, now what we are doing, we are providing two 16 mm dia bars throughout the whole beam at the top, and two 12 mm dia bars we are providing throughout at the bottom of the beam, right? Now what we do, the remaining 116 mm and 120 mm dia bar are, we are curtailing it over here and over. Okay, so this is the distance for the curtailment, 1.25 meters from here, 1.25 meters from here, right? So, and over here we have four numbers of 12 mm dia bars. Over here also we have four number of 12 mm dia bars, which we are curtailing over here at a distance 0.15 L, that is 0.75 meters from support and 0.75 meters from support. Okay, so here there will be two number of 12 mm dia bars, right? Because we are curtailing two number of 12 mm dia bar over here and two number of 12 mm dia bar over here, so the remaining two 12 mm two numbers of 12 mm dia bar will remain over here, right? Now another important thing which you have to check is the spacing between the bars, right? The maximum number of bars over here, three number of 16 and one number of 20 mm bar, right? So this is our beam section over here. So this is 230 mm, side cover is 20. Then comes the reinforcement, that is stirrup, dia of stirrup. Okay, then comes the bars. Okay, so the clear distance between the bar should be greater than first largest diameter. 20 mm is the largest diameter, or 25 mm, that is 20 mm gravel plus 5 mm buffer, right? So that is equal to 20 plus 5 is equal to 25. right? So in this two, out of this two, maximum is 25. So our clear spacing between the two bars should be greater than 25, and our is 35.3. So it's okay, it's fine, right? So that is how we have to do the check, so that proper concrete is surrounded, bar is surrounded with concrete properly, okay? And this is the anchorage, okay, that we have to provide, which we'll see later, okay? Now moving forward, so first step, find the for the maximum bending moment out of all this, okay, you have to find the minimum depth required, okay? The maximum bending moment is 127.93, that is 127.93, okay? We know mu limit is equal to 0.138 fckbd square for m20 grade of concrete fe415, and for this steel the effective depth is capital D minus effective cover, that is 475. This is the depth we have, effective depth we are providing, okay? The required effective depth should be less than this, okay? So this is the formula for finding the required effective depth, okay, which is obtained from this formula, that is equal to 448.9, which is less than 475, right, provided. So we can say that our section is singly underreinforced section. This is what we have done the check, okay? Okay, so this is a stress strain diagram for singly underreinforced section. This is balance NA, and actual NA will be on the above the balance NA, right? So this is force C, this is force T, this is strain diagram, this is design stress strain diagram, right, for concrete, okay? So in case of underreinforced section, the tensile steel yields before the outermost fiber of concrete reaches the ultimate strain 0.0035 and will give you a tensile failure with enough warning. That's why we go in for underreinforced section, okay? Now you have to check how to find the effective span, okay? You have to find the effective span as per clause 22.2d of IS 456-2000, which states, frames, in the analysis of continuous frame, center to center shall be taken as effective span. So the effective span for beam 1, 2, 3 and 4 shall be taken as 5 meters, okay? Because center to center distance we just saw above in the figure is 5 meters. Concrete grade as per table 5, IS 456-2000, okay? Well, our conditions are, exposure conditions are mild, okay? So for mild exposure conditions, the minimum grade of concrete to be taken is M20, which you can see table 5, and nominal cover as per table 16 IS 456-2000, the nominal cover should be to be provided at least is 20 m minimum, okay, right? So what is nominal cover, right? So in this figure we can see nominal cover is the distance from the outermost face of the concrete concrete section, okay? You don't have to take plaster, you have to take the bare concrete face, okay, from there to the bottom of the stirrups in case of beams. So definition, actual definition is from the concrete face to the outer face of the outermost steel, okay? Over here the outermost steel is stirrups, okay? So that is your nominal cover, right? What is effective cover? Effective cover is the distance from outer face to the CG of the steel, okay? Over here the CG of steel is at the center of this round bar, right? So in our case, in this figure we can say nominal effective cover is equal to nominal cover plus diameter of stirrup plus half the diameter of the bar, okay? This is how we get the effective cover, right? Okay, we have provided our effective cover as 50 mm, which is found to be okay, right? Check for lateral slenderness, clause 23.3 IS 456-2000. The code says the clear span of the member should be less than 25b or 250b square by d, whichever is less. Our clear span is 5 meter minus 0.45 meters. This is the depth of columns. So the clear span of beam is in longitudinal direction is 4.55 meters, which is less than 25 into b, that is 5.75 meters, and this 250b square by d is 27.84 meters. So our clear span is less than both these two, right? So we can say that the provided width equal to 230 mm is okay, okay? Now check for shear. Now First we will take left support of B1 and B10 and right support of B2 and B9. Okay, let me show you the figure. Okay, shear, this is B1, this is B2. Okay, the shear at left hand support of B1 is equal to the shear of right hand support of the B2. Okay, shear at the right hand support of B1 is equal to the shear of the left hand support of the B2. Okay, similarly B10 and B9, right? So shear force at left is 110, which we found from analysis. Okay, so we will do the check for shear. Okay, left support shear is 110, right? So we will first find the nominal shear stress, tau v, right? Tau v is V divided by BD. Okay, so this is V, this is BD. So this is found to be 1 Newton per mm square. Now tau v should not be greater than tau c max. Okay, if it is found to be greater than tau c max, then you will have to revise your section. Okay, so tau c max is 2.8 Newton per mm square for M20 grade of concrete. You can refer to table 20 of IS 456-2000. Okay, so tau v is less than tau c, so it's okay. Now next we have to find the permissible shear stress of concrete, that is tau c. For that we have to find the percentage of tensile steel at the corresponding section. Okay, so at the corresponding section where we are doing the check for shear, the tensile reinforcement is 402, that is EST negative left. We can see in the table. Okay, at left hand support the steel is 402 mm square, right? So for this area of steel, this is the formula for finding PT, 100 AST divided by BD. So we get PT as 0.368. Okay, so for the percentage 0.368 and M20 grade concrete, referring to table 19 of IS 456-2000, we get tau c is equal to 0.422. Now as tau c is less than tau v, okay, tau v is 1 and tau v is less than tau c max, so we will have to provide shear reinforcement for a force VUS, which will be taken by the stirrups. Okay, so finding for VUS, this is the formula given in the code, that is V left minus tau c BD. Actually it is V minus tau c BD. Over here we are denoting this as V left, right? So this is equal to 63.98. Now once you know this, you can find SV left, right? Put the value of VUS over here. The formula is 0.87 Fi ASV D divided by VUS. Please remember, this formula is only applicable to vertical stirrups, okay, and not inclined stirrups. As we are providing vertical stirrups, so we are using this formula. So ASV is the area, total area of legs of stirrup. We are providing 2-legged 8 mm dia stirrups. So area of 8 mm dia is 25.28 into 2 is 100.48, right? So this is how we get the spacing 269.33 mm center to center. Now as according to clause 26.5.1.5, the spacing of stirrup should be less than lesser of the below. Okay, these are the three conditions. One is 0.75 D, that is 365.25, 300, and SV is equal to this, right? So that is 394.33. Our spacing is found less than all the three, so we will provide 2-legged stirrups about 250 mm center to center for a distance of 1.25 meters at the from the left hand support. Okay, so let us see in the detail over here. For a distance of 1.25 meter, 8 mm dia stirrups about 250 mm center to center. Same thing we will provide over here also, right? Now moving forward. Okay, now check for shear at the right hand support. Okay, at right hand support the shear is 139.915. okay, so we will take that as VU right over here. Okay, VU right is 139.915. okay, so tau v is found to be 128, less than tau c 2.8. so okay, Okay, so we have to find now PT for the tensile steel at the considered section. Okay, so AST right support is 917 mm square, right? So we will find PT for that area of steel. The PT is found to be 0.839. Okay, the corresponding tau C is found to be 0.58 for M20 grade concrete, table 19 IS 456 2000. Now tau C is less than tau V, and tau is less than tau C max. So we will provide shear reinforcement for a shear force VUS that is equal to 76.55. Okay, so put the value of VUS over here. We get spacing as 2 to 5. This spacing has to be lesser of this 3, which is less. Okay, this is 56, this is 300, this is 394, right? So we will provide two leg stirrups about 200 mm center to center from the right support for a distance 1.25 meters. Okay, so this is what we provide, 8 mm dia about 200 mm center to center. Okay, as we just calculated, right? Okay, now as we know that as we go towards the center, the shear force reduces. We can also see the shear force diagram. Okay, as we move towards center, we see the shear force gets 0 at one place, right? So in this in between area, we will provide minimum stirrup. The spacing will be minimum. Okay, nominal stirrups has to be provided in that area. Okay, so the minimum spacing that I mean maximum spacing of stirrups that you can give is 300 mm, right? The maximum spacing that can be given is lesser of these three. So this is 356, this is 300, this is 394. The maximum spacing of stirrups you can give is 300, but we will provide 275, right? We will provide two leg stirrups about 275 mm center to center, right? So this is how we provided this stirrups, that's 8 mm dia stirrups about 275 mm center to center in the remaining in between area. Okay. So after doing the check for shear, now we have to do the check for deflection near the midspan where the positive moment is maximum. Okay, so the maximum positive steel provided at the midspan is 452, which we got from the table. Okay, positive AST near midspan 452, right? So we will find the percentage of steel for that. The corresponding percentage of steel 100 into ST divided by BD is 0.4137. Okay, so this is the formula given in the code. Okay, for deflection, we have to calculate KT and KC. KT is the modification factor due to the percentage tensile steel, and KC is the modification factor due to the percentage compression steel. Okay, so for finding this modification factor KT, we have to choose a graph. Which graph we will use? Okay, for that we have to find Fs. So the formula for Fs is given in the code, 0.58 Fi into area of steel required divided by area of steel provided. So area of steel provided is 452 and area of steel required is 431. Okay, we can see in this table area of steel required is 431 and provided is 452, right? So this is how we get Fs is equal to 2 to 9.51. Okay, but over here there is no graph for 2 to 9.51. So we will take a graph of higher value, right? That is Fs 240. So we will use Fs 240 graph. Okay, so this is PT. Okay, PT is 0.4137. So you have to just draw a line from here till this graph and you get the modification factor KT. Okay, so KT is found to be 1.35. Okay, now we are providing compression steel which will be considered as hanger bar. Okay, because at the midspan the section is singly underreinforced section. So though we are providing the compression bar at top, we are, of course, this assumption is a little bit on the conservative side, okay, but still we are not considering that top bars are taking any part in taking the resistance moment, right? So we are assuming that there is no compression steel, and the steel which is provided at top are hanger bars, okay, just to keep the stirrups in position, right? So when the compression steel percentage of compression steel is 0, the factor Kc is equal to 1. So we are taking Kc is equal to 1. Now from clause 23.2.1 IS 456-2000, L by D ratio allowable is equal to L by D basic into KT into Kc. For continuous beam it is 26, KT is 1.35, Kc is 1, this is 35.1, and L by D actual is 5000 by 475, this is 10.562, which is less than 35.1, so it is found to be okay in deflection criteria, right? Okay. Now, development length in tension when the concrete grade is M20 and grade of steel is Fe415. This we have to refer table 65 of SP16. Okay, this is a small part of that table. Okay. This anchorage bar, the anchorage to this bar should be at least equal to the development length for the bars in tension, okay, though this bar is in compression, okay, but still we will provide the development length for this bar as per bar in tension, because in case of earthquake the stresses can be reversible, right? So this, at that time, this might go under tension, right? So for 12 dia bar, that is this bottom bar, the development length required, minimum development means minimum anchorage length, you can say, to be provided should be equal to or greater than 564, which is obtained from this table. This is in centimeter, this is in mm, okay, and for 16 dia bar, okay, it should be 752. That is also obtained from this table, M20 grade concrete, right? So this is how we provide the anchorage length, okay, using this table, okay. Code says when the depth of the beam is greater than 750, then we have to provide side face bar as per clause 26.5.3.1 IS 456-2000. Side face bar, that you have to provide face bars, right, over here. But in our case, our beam size is 525, which is less than 750. Okay, so we don't have to provide the side face bars. This face bars helps in control of crack width on the side face of the beams. Okay, so this is how we design the complete design of that considered beams. Okay, now let us take another beam, that is B5 and B4. Okay, that is B5 and B4. Okay, this is B5 and this is B4. Now we are doing the design of this continuous beam. Okay, you can say. So all the steps remain the same. Okay, but over here we can see that in these are the beam number and their sizes. This is the moment at left, this is the moment at mid span, okay, and this is the moment this is the moment at right hand support. Okay, we can see over here the design moment is found to be greater than mu limit. Mu limit was 143 as we just calculated above, and this is 253. Okay, so we will have to go for doubly reinforced section over here. Okay, and in doubly reinforced section we will have both top steel and bottom steel, that is AST and ASC. Okay, in beam 4 at left hand support, again the moment is 253.87, which is greater than mu limit, so this has to be designed as doubly reinforced section. Okay, and other sections are to be designed as singly reinforced. Okay, let me show you this in the drawing. Okay, in the bending moment diagram. Oh yeah, this is B5, this is B4. This this moment is found to be greater than mu limit. This moment is found to be greater than mu limit. So this section and this section, this area of beam and this area of beam has to be designed as doubly reinforced section, right? This will be designed as singly under reinforced section, right? Because the moment is found, design moment is found to be less than mu limit. Okay, so let us first try to understand that how do we design a doubly reinforced section. Okay, so first step is at the the assumed section. Okay, this moment, okay, then these two moments and this moment. Okay, these four moments are found to be less than mu limit. Okay, so these four sections are under reinforced section. So you take the maximum out of this four moment, that is 134.25, and you find the required minimum provide depth, effective depth that is to be provided, right? In this case, our effective depth is equal to d minus effective cover, that is 475. This is provided, and the required should be less than provided. So taking the maximum moment, okay, we find d 459.88, which is less than 475. So the section is under reinforced at all the four cases, in that all the four cases, right? Now coming to this section and this section over here, right? Okay, I have made a note over here. The assumed section is singly under reinforced section about left support and the mid span of B5, and about right support and mid span of B4. Okay, on right support of B5 and left support of B4, the section is found to be over reinforced, and so we will design it as balanced doubly reinforced section. Okay, now how to do the design of doubly reinforced section. Okay, I have shown in table that AST found is 1756 and ASC found is 756. Okay, similarly over here also. So we will try to understand that how do we get this value. So this is the explaining diagram for a doubly reinforced section. This is doubly reinforced section, this is a strain. Okay, this is a balanced doubly reinforced section. This is the strain diagram. Okay, this can be divided into two parts. One is balanced singly reinforced section, and another is the additional steel to be provided to take the additional moment MA. Okay, so what is this additional moment MA? Okay, additional moment MA is design moment minus mu limit, that is going to be additional moment. Okay, so we will see that in detail. Okay, so the total steel AST will be AST limit plus the steel required to take the additional moment AST1 in tensile zone. So AST is equal to AST limit plus AST1, and AC is provided over here, right? So let us go step by step. Okay, first you have to find XU max. Okay, it's simple, as this is a balance section, so XU max is equal to 0.48D for Fe 415, so that is equal to 228 mm. Okay, now next step is for finding AST limit. First we should know mu limit, right? So mu limit, we know the formula, that is 0.138 FCKBD square, that is equal to 143.226. Okay, now once we know the mu limit, it's very easy to find AST limit. Okay, we know C, this is C, this is T. T is equal to 0.87 F5 into AST limit. We know mu limit, so T into lever arm is equal to mu limit. So T is equal to 0.87 F5 into AST limit. So AST limit is equal to mu limit into divided by 0.487 F5 into lever arm, right? This is lever arm. This is lever arm, right? So we know XU max. Put the value of XU max over here, and we get AST limit is 1044, right? Okay, I have written over here negative because ours is a hogging moment. Okay, so in our case the tensile steel will be at the top of the beam. Okay, and so you have to reverse this diagram. Okay, now So AST limit is 1044 mm square. So we have found AST limit. Now we have to find AST1. Okay. So for that we have to find additional moment MA. So our design moment is 253.87. So MA is equal to design moment minus MU limit. MU limit we have just found is equal to 143.22. So MA is 110.64. Okay, this is 110.64. Very easy. How to find AST limit? We know the stress in this bar. It is 0.87 F5. So we know the force TT 0.87 F5 into AST1. Okay, that is TT, right? And TT into lever arm. This is lever arm, right? D dash is the effective cover in the compression zone. So this lever arm will be D minus D dash. So this is D minus D dash. Okay. So T into JD is equal to MA. So T is equal to 0.87 F5 AST1, and this is lever arm, right? So we get the formula. AST1 is equal to MA divided by 0.87 F5 into lever arm. So that is equal to 721.079. When you add this and when you add AST limit, this you get total AST, that is 1756. Okay, this is how we got 1756 over here. Okay, so this is how we found AST. Now we have to find ASC. Okay, we have to find ASC, right? So first we will find force TT. We know AST1. Okay, 0.87 F5 into AST1 is equal to TT. So TT is found to be 260.345. Now from equilibrium CC is equal to TT. So CC is equal to 260.345. Now we want to find ASC. The stress into AC is equal to CC. So AC is equal to CC divided by stress. So we first have to find the stress in the compression steel. How to find the stress in the compression steel? Then we can find the stress in compression steel through strain. First find the strain at this level. Okay, this is a strain diagram. Find the strain using this formula. Okay, so the strain is found to be 0.00274. Once you know the strain, use table A of SP16 and you can find the corresponding stress from that table. The corresponding stress is found to be 535.31 Newton per mm square. Now this stress is for the tensile steel, okay, but our steel is compression steel. Okay, now we will have to reduce the concrete stress from the stress which we obtained, because this area of steel is replacing some area of concrete in this region, right? So the final stress will be taken as Fs minus 0.447 FCK. This is stress for the concrete, right? So this is Fs minus 0.447 FCK, that is equal to 344.37. This is our final stress in the compression steel over here. Now you know this, you know the stress, you can find ASC. CC divided by stress is ASC. Okay, so CC divided by Fs is equal to AC, that is 756 mm square, which we have written over here in the table, right? Okay, now these are the required area of AST and ASC. So we will provide three numbers of 25 mm dia bars plus 120 mm dia bar whose area is 1786 greater than 1756 required. Okay, 1756 required, right? And in AC we will provide 225 mm dia bar whose area is 981.25 greater than 756 required, right? 756 required. Okay, now a question comes in our mind that this is a balance section. When we provide steel larger than the balance section, then this definitely the section will become over reinforced. Okay, but on the other side we are providing a larger area of compression steel which will shift the neutral axis toward compression phase. Okay, which will make the section under reinforced again. Okay, so this is a very important point. Okay, so now we have derived the longitudinal steel area. So let us see the detail. Okay, beam B5 at left hand support we are providing 225 mm dia bars. Okay, so At left end support 225 mm dia bars. At mid span we are providing 225 mm dia bars. Okay, so 225 mm dia bars. And at right end support we just found, okay, we are providing steel as 325 plus 120 mm at top and 225 at bottom. Okay, so 325 plus 120 mm at top and 225 we have provided at bottom. Okay, so in the bottom 225 mm dia bars are running through the whole beam. Okay, and at top we are curtailing 125 and 120 mm bar at a distance 1.5 meters from here and here. Okay, otherwise 225 mm dia bars are running through the whole beam. Okay, similarly, important check over here, the spacing between the clear spacing between the bars should be greater than largest diameter of bar is 25 or 25 mm. We are providing 26.3, so it's okay, right? So this is how you do the detailing of the longitudinal steel. Okay, now coming to the next step, that is check for shear. Okay, first we will see this effective span as seen above. We are taking 5 meters, that is center to center. Okay, and the concrete grade for a mild exposure has to minimum concrete grade is 1020 and minimum nominal cover is 20, which we have satisfied. We are taking effective cover as 50 mm. Okay, check for lateral centeredness as per clause 23.3. Clear span should be less than 25b or 250b square by d. Okay, over is 455, less than 5.75 and less than 27.84. So we are providing width equal to 230, which is found to be okay. Check for shear at left support. This is the V left which we get from analysis. Sorry. So tau V is found to be 2.026, which is less than tau C 2.8 for M20 grade concrete, table 20 of IS 456 2000. Okay, tau B should be less than tau C max, right? Now we want to find the permissible shear stress tau C. So the steel provided on the left hand support, okay, steel provided on the left hand support is 981.25. Okay, so 981.25, okay, is the steel. So corresponding PT from this formula we find 0.898. So tau C corresponding is 0.6. This tau C is less than 2.026 tau V. Okay, and tau is less than tau C max. So we will have to provide shear reinforcement to take the additional shears VUS. VUS is found to be 155.835. Put the value over here. We find the spacing of stirrups required as 110. Okay, we are again using two-legged 8 mm stirrups, right? This spacing should be lesser of this three. This is 356, this is 300, and this is 394, which is less than all these three. So we will provide two legs 8 mm dia stirrups about 100 mm center to center for a distance 1.25 meters from left. Okay, we will see in the detail. 8 mm dia about 100 mm. Okay, on left. Okay, so this has to be provided here also, right? Now coming to the right hand support, right? Check for shear at right hand support. This is way right. The tau V is found to be 2.55, less than tau C max 2.8. So okay. Now the steel provided at right hand support is, okay, we just found over here 1786. Okay, so we are taking 1786. Okay, so PT from this formula we find it as 1.635. Corresponding tau C is 0.735. Tau C is less than tau V and tau V is less than tau C max. So we will provide shear reinforcement for the additional shear VUS, which has to be taken by shear reinforcement, that is equal to 198.315. Okay, so the required spacing is found to be 86.89 for two-legged 8 mm stirrups. Okay, this has to be lesser of these three, which is less than This is 356, 300, and this is 394. So we will provide two-legged 8 mm stirrups about 80 mm center to center for a distance of 1.5 from right. Okay. So that is what we are providing at about 80 mm over here and over here, right? And we know that as we move towards center, the shear force decreases. Okay. So in this between area, we will provide 8 mm stirrups about 150 mm, 150 mm. Okay. Alright, now one important thing which we have to keep in mind when the section is doubly reinforced. In the region where the beam is doubly reinforced, the spacing of stirrups should also satisfy the criteria for ties in compression member. Okay, in doubly reinforced we are having compression steel. Okay, if you don't satisfy the criteria for ties, then there are chances that the compression steel will buckle out. Okay, the spacing of the tie taken should be list of the following. D, our D is 525, 16 into the smallest diameter of the bar, that is 16 into 12 is the smallest diameter, that is 192, and 300 mm. We are providing 80, which is less than 3, so it's okay. Okay. Now another point is the diameter of the stirrups which you are using should also satisfy the tie criteria. The diameter should be greater, at least a larger of these two. Okay, 6 mm or larger bar diameter divided by 4, that is 6.25. We are providing 8 mm, so it's okay. Okay, this is very important when you are designing a doubly reinforced section, right? Okay. Okay, this we already seen. In remaining middle portion, we are providing two-legged stirrups about 150 mm. Okay, now check for deflection. Okay, so we will check the deflection near the midspan where the positive moment is maximum. The positive steel provided is 981.25. Okay, that is 225 mm diameter. Okay, simple. So PT corresponding is 0.898. Fs is found to be 235. So there is no graph for 235. So we will take a graph for a larger value of Fs, that is 240, and find KT. Okay. So this is 0.898, so around about 0.9. So when you take this is KT is found to be 1. Okay, so KT is found to be 1. KC we are taking 1. Okay, from clause 23.2.1 IS 456 2000, L by D allowable is equal to L by D basic into KT into KC. This basic is 26, KT is 1, KC is 1, this is 26. L by D actual is 5000 divided by 475, this is 10.562, 526. Okay, this is less than 26, so it is found to be okay in deflection. Okay, now development length, this is 25 mm bar, this is 25 mm bar. So the development length or anchor length that you have to provide should be at least 1535, which we found from this table. Okay, when the depth of the beam is greater than 750 mm, then we have to provide side face bar. Okay, but our is 525, so we need not provide the face bar. Okay, so now coming to the last set of beams, that is B11, B6, B8, B3. Okay, the design procedure is the same. You just have to follow the same procedure. Okay, nothing is same and nothing is changed. Everything, all the fundamentals remains the same. Okay, I am just showing B6. Okay, B11, and this is B6. This is B8. This is B3. Okay, so we are designing that set of beams. Okay, so I will move fast because now we know the fundamentals. I will just brush up the things. Okay, for these beams, right? Okay, so B11, B6, B8, B3, these are the beam sizes. Okay, now the beam is 230 by 300, right? So at all the sections, the section is found to be under reinforced. Find this is the formula for MU limit. Our effective depth over here is 250 mm. Effective depth required for the maximum moment out of this, all the moment, okay, is 27.26. We find D 207.25. Provided effective depth is 250, so required is less than 250, so the section is singly under reinforced. Okay, right? Check for shear. Okay, tau V is found to be 0.875, less than tau C max. Okay, tau C is found to be 0.525, which is less than Doubly. So additional shear reinforcement has to be provided. VUS for VUS is equal to 20.15. Okay, so spacing found required is 450. This spacing should be lesser of this. Okay, over here 0.75D is 187.5, this is 300, this is 394. So now we have to provide spacing of stirrups less than 187. So we will provide two leg stirrups about 175 mm center to center. Okay, for on the left hand support. Similarly on right hand support also we get the same spacing, and we will provide the same spacing in the mid span also, right? So this is the longitudinal steel detail. Okay, we are providing two 12 mm dia bars throughout the whole beam, and one 10 mm dia bar which is curtailed at a distance 0.75 meters, and at bottom we are providing two 12 mm dia bar throughout the beam. Okay, and stirrups we are providing 8 mm at spacing 175 center to center for the whole beam. Okay, right. Now check for deflection. AST at the midspan is 212 mm dia bars. The area is 226. So PT is 0.393. FS is found to be 189. So the larger FS, next larger FS is 109. Okay, we have a graph of 190. Sorry, not 109, 190. Right. So we will use this graph. Right. So we know PT is round about 0.4%. Okay, so when you come here, we get KT is equal to 1.625, right? KC we are taking as 1, putting the value over here, we get ratio L by D allowable as 42.25. This L by D actual is 12, which is less than 42.25. Okay, so the section is safe in deflection. Okay, and then again the development length. Okay, we have 12 mm dia bar. Okay, so for 12 mm dia bar, the development length, anchorage length should be at least 564. Okay, this is the minimum that you have to provide, right? And when the depth of the beam is greater than 750 mm, we have to provide face bar, but our beam depth is 300, so we don't have to provide the face bars. Okay, similarly you can design the beam B12 and B7 with the same fundamentals. Please visit the website mmsprogramcivil.com for all the videos and PDF. I hope you must have found this video useful. Thank you.